using the projector today because it doesn't exist. In that whatever machine it is that like connects the computer to the projector just isn't turning on. I've tried putzing around with it, but and by the time I call LTS, like they'll show up too late anyway. So I'm gonna use this. So I'm gonna go through the same stuff we have. So let's start with this. Do we want another example of just graphing a polynomial that's been factored? Is there demand? Yeah, cool, let's do it. So this example is just writing your notes, page 65. Let's graph this function. Sure. Oh, this is this. No, if that's the case, then I think we've done both of the examples that I had at least prepared in the notes for graphing high-degree polynomials. Yeah, I mean, I don't know. I guess the question stands though, is there still demand? You want one done? You can tweak this example. Yeah, all right. Let's do it. Let's change this in some. There, this should do. So, we'll ask the same questions as we did before. We will locate the x-intercepts. We'll locate the y-intercepts. Y-intercepts are pretty boring for this one. We will identify the local behavior near each of the intercepts. We will decide what happens when x is big. And we'll go from there. So, proceeding. Where are the x-intercepts? And maybe more useful than just writing those down. How'd you find those? Like, how did you identify those?
By plugging in the function, so each term is 0.
Yeah. X squared is 0, that just becomes x equals 0. 2x minus 3 squared equals 0. I guess that means 2x equals 3, x equals 3 halves. If you like decimals, then that's 1.5. And that's even exactly equal to. Or 1 minus x equals 0, so x equals 1. And let's put them on here. Origin. (1.5, comma 0) and 1, comma 0. Neato. So far, so good? Now let's play this local behavior game. Oh wait, y-intercept. Do we even need to do any work to find the y-intercept this time? Or just where's the y-intercept? 0, 0. Because we've already seen where it crosses the y-axis, it has to go through that point. All right, local behavior near each of the intercepts. So close to each of the intercepts, the local behavior is given by remembering the factor that causes that x-intercept, and then plugging x equals that x-intercept value for all of the other x's in the formula. That's what the informal statement of this theorem we have says. So let's do that. Close to x equals 0, I need to remember the x squared. Now I'll plug in 0 for all the other x's. Oh, but that gets squared. All right. So the x squared says it's a parabola, upward opening or downward?
Upward.
Upward, because 3 squared is positive. Close to the next two intercepts. Well, what do you think? Should I do the walk, or would it be more effective if I were just quiet for a bit and you told me? People want me to do walk? Cool. Then I will pause for a bit. Close to each of these. Get something like that and put something on the resulting graph. So as you resolve what the local behavior at one of those intercepts is, go ahead and throw it on the graph that you're sketching. And then also, tell me about it. Tell me some of the local behavior of this function. Let's see, so for the x equals 1, it looks like I need to remember the 1 minus x, because that's the factor that's actually 0. So I'll remember that. So by default, that's already going to be like a negative slope right now. Let's see what it gets multiplied by. I'll plug in 1 for all of the other x's. Okay. Biggest degree I see is 1, so it's going to be a line. Is the slope going to be positive or negative?
Negative.
I hear a negative. Do I hear a second? Cool. Add that to the graph. Close to x equals 1.5. Let's see, the 1.5 came from the square talk, so it's going to be a parabola. But you tell me, upward opening or downward? So you plug in x equals 1.5 for all of the remaining x's. The resulting coefficient positive or negative? .5 squared, positive or negative? That's the piece I just need to remember. 1 minus 1.5, positive or negative? So in total, the coefficient is, okay, cool. I know that felt an awful lot like pulling teeth, but you can just tell me. So let's put the parabola there. Next step, interpolate smoothly between. So it looks like there's going to be like a hump and a valley. I have no idea how big they're going to be because I'm not checking that. When x is big, so you take a look at that thing. What's the degree of that polynomial in total? I think 5. So this thing is degree 5. And you can get the asymptotic behavior by forgetting all but the biggest term of each factor. X squared, that's just an x squared. 2x minus 3, the minus 3 doesn't make a difference. One minus x is pretty close to just being negative x. seem okay? And I know this room's an absolute nightmare. When the projector doesn't walk, I can't do anything about the stair there. Two x squared. There we go. If I avoid that, can everyone actually see what's on the board if I just avoid that chunk? Okay. All right, so degree 5 polynomial, but there's a negative in front of it, so it should look like an odd degree polynomial, but flipped over the x-axis. Cool. That feel pretty okay? Nice. So if you want to graph a high degree polynomial and it's factored, then you can do it more or less algorithmically. Figure out the roots from each factor, figure out the local behavior by looking by what happens because of each factor, interpolate between, figure out the asymptotics. But there's like an issue here, right? Usually when you see a high degree polynomial, x to the 5th plus 4x squared plus 2x plus 1, it's not factored for you. Because you So what can you still do to try to factor such a thing? So this is where I'm going to start in on the next section. Section 3.2, some tricks for solving high degree polynomial equations. So, this problem, solving high degree polynomials, is an important problem in mathematics. A significant chunk of the development of algebra is built around this question. And the resolution is less than satisfying, but it is a surprising resolution, which is nice. So first of all, if you have a degree 1 polynomial, is that easy to solve, easy to set equal to 0 and solve? Yeah, right, mx plus b, there's only one x, get x on its own. Degree 2 polynomials, are those easy enough to solve? Yeah, you got a quadratic formula. In fact, the quadratic formula, there's evidence that it was known at least at the time of the construction of the pyramids. They would have thought of it very much differently because that also predates the Arabic numeral system that we use. Degree 3 polynomials, it turns out those can be solved by a formula. That formula is due to a mathematician by the name of, is this Cardano? Yeah, Cardano did the cubic formula in the 1500s. With some following work by another mathematician by the name Tartaglia. Shortly after that, that was Cardano. Ferrari produced the quartic formula. So every degree 4 polynomial has a formulaic solution. The reason you've never seen these formulas is the cubic formula probably takes a couple of lines of paper to write down. You need to really write some words to describe it. If you go and read the Wikipedia article, you can parse out what it's saying. So you can get the cubic formula. Quartic formula, if you want to write it down, it probably takes a little bit more than a page to write down the details of what the formula says. So that's what you don't know. It's too big to really use easily anyway. In the 1800s, a mathematician by the name of Galois proved the following. If you have a degree 5 polynomial, there is no guarantee that there's even a way of expressing the solutions to that degree 5 polynomial using any combination of algebraic doodads. So any combination of plus, minus, square root, nth root, raising things to powers, there's no guarantee it's even possible. In fact, here's an explicit polynomial for which it is not possible. X to the 5th minus x minus 1, that has no algebraic solutions. So, it has solutions, but you can't even express them using algebraic techniques. So, that means that what I'm going to try to do today is kind of doomed to failure from the start, because I'm going to try to solve polynomials using only algebraic techniques. So let's just keep in mind that there are non-algebraic techniques. There's a polynomial in there, and people have graphing calculators on them. given that hint, do you think you could use that tool to approximate the solutions to that degree 5 polynomial? Yeah, do it. I guess if you don't have a graphing calculator, but you do have like a laptop you're going to class. Generally, I'd like to be doing this using the projectile, but I can't. So once you have a graph pulled up of this degree 5 polynomial, tell me some things about it.
It goes through that x-intercept once.
Goes through the x-intercept once. So that means there is one real solution.
Yeah.
About where is that?
1, right, 1, 6, 7.
Gesundheit. And like, I don't know, it does something like that, right?
Yeah.
Cool. So if I ask you what the real solutions to this degree 5 polynomial are, you can't tell me anything exact about using this graph, but you can tell me that it's pretty close to 1.167. So keep in mind, if you want to solve a high degree polynomial using only algebra, there's a chance that you just can't. There's a chance that you need to use something like a graphical technique to do it. There's some really good tools that you'll want in calculus for solving such a thing. In calculus, get good at approximating any function with a line. So one thing you can do, if you start at any point on the graph, you can approximate this with a line. You can figure out where that hits the x-axis. Oh, now you can just use that same x value, figure out where that hits the x-axis. You can get as good as you want using that. In fact, that's a lot of computer techniques do things like that when you ask them to solve complicated equations. Neato. Newton's method. Okay, but I still want to try to make some progress. So what I'm going to try to build today is some tricks that apply sometimes that can help you solve high degree polynomial equations. And I think the right place to begin is just let's try to solve one and we'll develop some tools. I can erase this one now. So let's see. Here's a question. There's a degree 3 polynomial equation. I'm going to ask you to solve it, but I'm giving you one fact for free. X equals 1 is a solution to that equation. In fact, check that real quick. When you plug in x equals 1 to that thing, do you get 0? Ooh, and those of you who are using a calculator to do this are making it harder than it needs to be. Plugging in 1 is like the easiest thing. Second easiest, 0 is easier. Any power of 1 is just 0. So to plug in 1, you just add up the coefficients. So when you plug in 1, you'd get 2. Ooh, that's embarrassing. 2 minus 1 minus 7 plus 6. That works out to be 0, I hope. Cool. So x equals 1 is a solution. Here's the thing that you can know as a fact because of this idea. So factors of a polynomial correspond to roots. We can do the opposite. I know that x equals 1 is a solution. So x minus 1 So x minus 1 has to divide evenly into that thing. So I'm going to describe what this means. So 2x cubed minus x squared minus 7x plus 6. You can rewrite that as x minus 1 times times some polynomial. What would the degree of that something have to be? What's the total degree on this side?
3.
3. This is already degree 1.
It'd have to be 2.
Degree 2. I can solve a degree 2 polynomial. So if I can figure out this something, then I can know that x equals 1 is a solution. I can set this equal to 0. I can use the quadratic formula. I'll be done. So the hard part here is just figuring out what that something is. It's factoring this polynomial. And I don't know, like this is kind of an edge case of what people either are or are not familiar with. Anyone in the room just already feel positively about factoring polynomials like this? Anyone feel like it's something that they've seen before and like have done at some point? Anyone feel like they don't know what the word factoring means in the context of polynomials? Okay, cool, because like that's what factoring means. I need to express it as a product. So I'm going to do this 3 different ways, and now it's like the 3 different columns in the notes on page 66. There are 3 different philosophies that you might have with factoring. The first is the most intuitive, but it's also the most walk. The middle one is polynomial long division. It's less walk than this like ad hoc factoring that I'll do on the leftmost column. But as long as you remember what long division means for numbers, you can figure that out. Synthetic division abbreviates all of the walk and takes up no space, but if you don't already know what all the symbols mean, it is absolutely unreadable. So depending on how compact you want to be in notation, we'll do all 3. Let's start with factoring by grouping. So here's the polynomial I want to do stuff with. So I remember that I really want x minus 1 to factor into all of this. So let's see, if I saw like this 2x cubed minus 2x squared, I could factor an x minus 1 out of that piece if there were just a 2 in front of this, right? Right, then I could factor a 2 out of just this piece, I could factor out the x squared, I'd be left with x minus 1. But I don't see that 2x squared, but I could. Right? One strategy, if you don't see something that you want in an equation, just put it there. Just make sure that you also anti-put it there. So let's do that. This is the exact same thing as, I'm going to try to do some color coding. 2x cubed, I'll just have there already, minus 2x squared plus 2x squared, minus x squared minus 7x plus 6. Do you agree that those 2 things are equal? Right, you can always add and subtract the same something. Those 2 terms would cancel, but I don't want to cancel them because I put that 2x squared there for a reason. Now I'm going to focus on that piece. Let's say I can factor out 2 out of that piece, but everything has a 2 next to it. Everything has at least 2 x's in it, so I can factor out an x squared. When I factor out that x squared, I'll be left with x minus 1, which was the whole reason I put that piece there. And now, we'll just keep marching down the terms. I guess we better simplify. 2x squared minus x squared, what does that simplify to? It's just x, it's just x squared. Oh, I want to switch colors back to yellow. And I'm intentionally leaving myself space here. All right, so, oh, don't need a double plus sign. Again, I want to factor out x minus 1 out of the whole thing. So if I saw like a minus x here, that would make me happy. Do you see a minus x next to this thing? Yeah, the truth is like either answer of yes or no would be right. So you said yes. Why do you see a minus x next to it?
see minus x on top of it, like minus x squared.
Oh yeah, that's the previous line now. Because that minus x squared and the plus 2x squared, those came together for this.
Okay.
So I need a minus x squared in this line.
Okay. Just make one.
Yeah, we could just make one, right? Just put a minus x next to it and then add x. And the whole point of doing that is so that I can do some factoring. So let's do that. And now we'll just do the same thing as we did before. This already has an x minus 1 factored out of it. That piece makes me happy. This next piece there. Could you factor an x minus 1 out of that? Yeah, it's the whole point of putting those things where they are. So let's just write the next line then. Equals 2x squared, x minus 1, plus x times x minus 1. X minus 7x leaves me with minus 6x plus 6. There's the last piece I need to worry about. Minus 6x plus 6. Does that factor in any nice way?
Six.
I could pull a 6 out. I think I'm even going to pull a minus 6 out, so I get an x minus 1. Right, it would just flip the sign on the other 6. All right. So, equals minus 2x squared, x minus 1, x plus x times x minus 1, minus 6 times x minus 1. Everything now has an x minus 1 next to it. Oh, neat. Have I now factored an x minus 1 out of everything in that polynomial? So that means I know what that something is. This something appears to be 2x squared plus x minus 6. How does this process feel? So there's no fancy ideas here. You just think about what you would want to see next to the highest degree term in order to factor out whatever linear factor you want to factor out of it. And then you factor the piece out that you now know you can. You've now factored an x minus 1 in this case, but it could be an x minus 5 or 3x minus 2 out of whichever piece you're interested in. There's now lower degree pieces. Keep on marching down until you've eaten up everything. So there's this ad hoc technique that's just factoring by grouping. As you see, this takes up a fair amount of space. But each term, you need two ideas. You need to know that you can add and subtract things, and you need to know how to factor a linear thing out of like two terms next to each other. If you can do those two things, you can use this technique. Let's go on to the next one. So if I say polynomial long division, how many people would say that they've seen that at some point? How many people would say that they feel negatively about polynomial division? How many people would say they feel pretty okay about doing polynomial long division? Oh, cool. Let's do some polynomial long division, because that'll achieve the same goal. Right, whenever you want to write this as that times something, well, how do you find that something? You divide the x minus 1 to the other side. So you just need to know how to divide a polynomial by another. There's an algorithm that does it called polynomial division. We'll do one example right now. How many people think they'd like to see like basically a full lecture length thing on just how do you do polynomial division? Cool, that appears on the course web pages of a recorded video. There's like a section in the notes that's a couple of pages on it. And it's on the course web page already because it's recorded in the past. So let's do some polynomial long division now. So if you want to compute this divided by x minus 1. So this is down like the middle column in the text. there's an algorithm that we'll follow that's going to be very much inspired by just long division of numbers. So how do you do long division of numbers? You ask yourself how many times the thing here divides evenly into, not evenly into, just how many times does it divide into the biggest piece inside of the box. We'll play the exact same game here. We'll look at the biggest piece there and the biggest piece there, figure out how many times it divides evenly in. We'll have to do some subtraction. And then we'll update and do it again. So, let's do it. What do you need to multiply x by to get 2x cubed?
2x, 2 cubed.
Yeah, 2x, but you need 2x's, so 2x squared.
Oh, yeah.
2 for the 2, x cubed is x times x squared. Nice. So that tells you what the biggest piece of the polynomial is. It's going to be 2x squared. And just how like in long division, what do you do now? You take this, you multiply it by that, and you subtract the result. So this times that, and now you need to do subtraction. So 2x squared times x is 2x cubed, but I need to subtract it. 2x squared times -1 is negative 2x squared, but I need to subtract it so that minus becomes a plus. So far so good? All right. And you'll notice I'm going like really slow and taking long pauses. How many people who have already just completed this polynomial division already? Oh, cool. Did you get the same thing as we found for the something? Nice, that's important. All of these things need to give you the same result. So, carrying on, negative x squared plus 2x squared is x squared. And now we repeat. What do you need to multiply x by to get x times x?
X.
You need an x. Next one will be plus x, which agrees with what we have over there. And now we repeat the process again. Take x, multiply it by this, and subtract the result. So x times x is x squared, but I need to subtract it. X times 1 is negative x, but then I need to subtract the result, so plus x. So far going okay? So the reason this is a plus is because that's a minus, and I need to do multiplication and then subtract. So if it helps, write the intermediate step where you say x times x is x squared, x times 1 is minus x, but there should be a minus sign there. Then distribute the minus sign. Which you can only do if you like don't do your math in prominent pen, right? So minus 7x plus x leaves me with plus 6x. Nope, minus 6x. And now ask the same question again. What do I need to multiply x by to get negative 6 multiplied by x? Negative 6. Right, the answer is in the question. And now we repeat. Minus 6 times x is minus 6x. Minus 6 times minus 1 is plus 6. But I need to subtract that result. Distribute the negative sign. 0x. 6 minus 6 is 0. Which is good, right? I knew that the remainder shouldn't be 0. Right, like when you do long division and you know that this number has to divide evenly in, if you get a remainder term at the end, then like you screwed up. We didn't get a remainder term, so we're fine. So again, we get the same result of division. Yeah.
Would it be too much to ask to do another example of this?
Well, I'll tell you what, let me do, there will be one on the next page.
Okay.
Instead, I'm going to do another technique because, so the algorithm here is at each stage, decide what you need to multiply the biggest thing on the denominator by to get the biggest thing in the numerator. Do subtraction and then iterate. but you'll notice there's a lot of empty space here, and there kind of has to be. Synthetic division erases all of the empty space, encodes only the things you need to perform this algorithm, and is basically unreadable if you don't already know what it's supposed to say. So let's do some synthetic division. So to set this up using synthetic division, maybe here's something to appreciate. This took less space and less time than factoring by grouping, so we just had to write less. Synthetic division. So if I want to divide x minus 1 into this high degree polynomial, I'm only going to record the coefficients. 2, -1, -7, 6. You'll notice that every time that I did this multiplication, I took this, multiplied it by that -1, but then made it negative again. So I'm going to put a +1 there, which if you like is the root that corresponds to x minus 1. I'm just going to record that outside of the square that is synthetic division. And here's the algorithm that I'll now follow. You'll notice this 2 became that 2. So, synthetic division, the first step of the algorithm is just put that 2 there. The next step in the synthetic division algorithm is take these 2, multiply it by the 1, in the next column, add these 2 together to get +1. The next entry in synthetic division is +1. Plugging along okay so far? And now I'll do the same thing. 1 times 1 is 1, it goes in the next column. -7 plus 1 is -6. Next entry is -6. -6 times 1 is -6. So the remainder is 0. So, here's some things to notice. All of the actual addition and subtraction and all the multiplication that we did over on this side, we also did in that synthetic division box. But we forgot all of the context and just remembered the algorithm. And so it took less space and less time. The downside is, if you just do synthetic division, there's no way of detecting if you have an error in the algorithm other than just like manually checking if your multiplication is correct. But let's write down the conclusion in each of these cases. In each of these cases, (2x cubed minus x squared minus 7x plus 6 is equal to x minus 1 multiplied by 2x squared plus x minus 6. Each one of these gives you that same conclusion. Synthetic division says this 2 corresponds to a 2x squared, plus 1 for plus x, minus 6 for minus 6. Nice. Okay, why was this useful? Let's remember the problem we even wanted to answer at the beginning of this. So now I'm going to go to the space below those vertical lines. Let's find all of the roots of this degree 3 polynomial equation. Instead, I need to solve that degree 3 polynomial equal to 0 because, well, it's the same equation, right? This left-hand side is equal to that left-hand side. Does this look easy to solve now? At least easier? You all have very good poker faces, I can't read you. So if you wanted to solve this equation, what should you do? Yeah, quadratic formula, first you split it into two equations that way. So. Oh, cool, this one's easy. That's x equals 1, it's also disappointing because that's the one we already knew. That other one, that looks easy to solve though, right? That's quadratic formula?
You can factor that.
Oh, you could even factor it. How does it factor?
Goes into 2x minus 3 and then x plus 2. Or no, x minus, x plus 2.
Cool. So that means you also just know the roots. 1.5? You know. How many people use the quadratic formula instead? Oh, okay. It was quick, I guess. We've now found 3 roots. We expected 3 roots. This polynomial equation is now solved. So here's the game. As soon as you know one root, you can use factoring by grouping, polynomial long division, or synthetic division to reduce the difficulty of your polynomial equation by 1 degree. If you can get down to degree 2, or degree 1, I guess in this case we got all the way to degree 1, you can solve it. You can't always do that, but when you can, it's nice. So let's spend,
To do this, you need to know one solution.
you need to have an initial guess of a solution before you start. And that's a problem, right? You needed, like I didn't tell you how I got that x equals 1. And in fact, I got that x equals 1 by starting with something that I knew would factor, anti-factoring it, and then I knew there was an example that would walk out. In general, there's no promise that you can factor a high degree polynomial. So there's no promise that any of the techniques I'm going to teach you will apply in every example you have. They're good techniques to have because they give you lots of information, but they might not always solve the equation you want to solve. In this case, they did. But, I don't know, I think the right thing to do now is we've got like 6 minutes left on the clock. Let's do one more example. So on the next page, I see 2 more examples. A thing that maybe you would even want to call a cyclotomic polynomial, x cubed plus x squared plus x plus 1. Or 2x cubed minus 10x squared minus x plus 5. For both of those, I've given you one solution. So that should be enough to run this algorithm. Which one should we do? The first one on the page or the second? People have a preference? First one? Second one? Cool, let's do the second one. They'll both be exactly the same amount of walk. And maybe the second one is actually a little more walk because it just has more numbers in it. So, let's put that down. Let's solve 2x cubed minus 10x squared minus x plus 5 equals 0, given that x equals 5 is a solution. So the game is, I should be able to write this as x minus 5 times something. If I can find that something, I've reduced the degree by 1, I can use the quadratic formula, or maybe it factors. To find that question mark, we have 3 techniques. We can do this ad hoc factoring by grouping. We can do polynomial long division, or we could do synthetic division. Maybe I'll focus on the second 2 techniques, polynomial long or synthetic. And people would rather see this done by polynomial long division. Cool. And people would prefer it seen by synthetic division. How many people are just planning on doing it on their own using synthetic division? On their own with polynomial long? Cool. Synthetic division is the time-wise most efficient of the techniques. All right, so let's see, if I'm going to use polynomial long division, I need to do x minus 5. How many times does that divide into 2x cubed minus 10x squared minus x plus 5? Oh, maybe I should say this about synthetic division. If this in front of that x were a 2 instead of just a 1, synthetic division doesn't know what to do. It has to be a monic polynomial to do synthetic division. It's not though, so that 2 isn't there. So we could do synthetic division if we wanted to. So, now we'll follow the algorithm. What do I need to multiply this x by to get 2x cubed?
No, 2.
Not just 2.
X squared, yeah.
All right. Cool. So in synthetic division, that would just correspond to like a 2 showing up. And now you know what I'm going to do next. I'm going to take this 2x squared multiplied by x minus 5 and subtract the result. I have the ability to erase in chalk, so maybe I'll put the minus sign and then I'll distribute it. So I'll need to put here a minus 2x squared times x is 2x cubed. That's good, that's what I knew it had to be. 2x squared times 5 is 10 with a negative sign, x squared. We will now distribute that negative sign through it. Did I screw anything up yet? I'm getting some people who look upset. We're okay? All right. 0, ooh, negative 10x squared plus 10x squared is 0x squared. That's fantastic. What do I need to multiply x by to get 0 multiplied by x squared? Yeah, well in particular 0. Is 0 something? I don't know. You meant the right thing, I'm sure. There's nothing there. So you don't even need really the plus 0 up there. It's nice to have that plus 0 for like bookkeeping reasons.
The next one is -1.
I see a negative x here, so I need to multiply that by -1. Multiply -1 by this and subtract. I guess I even, well, let's use multiple space. Minus negative x plus 5. Distribute the negative sign. Oh, cool. So we're done with the polynomial long division step. And that's good, because I have a minute. I think I can wrap this up in a minute. So, instead we need to solve x minus 5 multiplied by 2x squared minus 1 equals 0. Does that look easy to solve? Yeah. So it looks like I see x equals 5, the thing I already had, and I need to set this equal to 0 and solve. I think I'm getting plus or minus root 2. Cool. Yeah, one should simplify. Like that? Or the square root of 1/2, but then you'd simplify to that. Neato. So, here are some things to advertise if you're feeling uncomfortable with polynomial long division or synthetic division. There's a good discussion in the back of the book, in the appendixes. Appendices? Whatever, don't care. That goes through a bunch of things about polynomial division. Go through that. It's a really powerful technique to have, but I also just don't have time in this class to like really give it more discussion than I spent on it today. Probably I spent more time on it than I should have today. So, in fact, what I'd like you to do, by the time we get here next, there's another example on page 67 of the notes. How many people have just already done that? Oh, cool. If you haven't, then do it by the time we get here tomorrow. Now, I'm going to call LTS. Which one? Yeah, sure. Describe it to me.
Oh my god. I don't know how to explain it. It's just like you just take the coefficient and then you with the number, like the multipliers of the last number, you try and plug them until, can I show you? I have the class now.
Yeah.
Okay.
Yeah, I
But
suspect
you
that
get all like,
what you're about to describe to me is equivalent to probably synthetic division, but I might be wrong.
yeah, similar.
Yeah, I think it's absolutely equivalent, it's just like organized in a different way. Yeah, yeah, show me the technique tomorrow,
Okay.
maybe right before our class starts.
Okay, okay.
Yeah.
Where do I go to find out when these
Do you have the syllabus on you?
It's in my bag.
Cool, there's a course webpage indicated on there.
Okay.
That's where the dates are.
Okay.
If you also just go into Canvas, there's like a logistics and announcements item at the top of the page. If you click in there, there's a course webpage.
Okay.
Yeah,
Thank you.
if I had, the projector running, I'd be able to show you, but.
Thank you.
Yeah.